Today's lesson is on the central limit theorem for sample means. And a big idea here is that the sampling distribution of the mean is always, or at least approximately, normally distributed. What do I mean by this? Here we have a sketch of how much tuition costs for a two-year college in 2012 to 2013 academic year. And if you notice about this sketch, which is all the populations, all the schools in the United States that are two-year colleges, it's not really normal, right? We have this, we have a tail, it's right skewed. It's not unimodal, it's bimodal, right? There's two humps, and it's not very symmetric. But what's interesting is when we start taking the means, right, a sample of the means, right, the sample mean distribution, right, this is the sample mean distribution. What happens is it starts looking a little normal, right? Yes, we still have a an outlier over here, but if we take another 30, it really starts looking normal, right? And if we take 90, right, a sample size of 90 colleges, it starts looking a little more normal. So, but there are three rules in order to assume that our sample mean distribution will be normal, meaning that we can use, the normal distribution curve to come up with the probabilities of events occurring in a sample. All right. So the first rule is that our sample has to be random and independent. Our second rule is it should be a large sample, meaning anything bigger than 25. And our population should be big. So our population, if we take whatever our sample is, right, and we multiply it by 10, right, our population should be at least that, right? Should be at least that. So it should be at least that or bigger, right? So let's look at some examples. But before we do, let's jump into just some things from last week. Last week, we learned that the standard error for these types of problems is the standard deviation divided by the square root of the sample size, right? And to draw the normal curve, we take the mean and we take the standard error where the standard deviation used to be to make our normal curve. Right, so our normal curve would have the u here, and now what we're going to start doing is our SE, we're going to add an SE, we're going to subtract an SE, right? And same thing here, it's the plus 2, the minus 2. All right, so at a race of several thousand people, the average finishing time is 91 minutes with a standard deviation of 16. The distribution is close to normal. Okay, with that, right, so here what we're learning is that the actual population is normal, right? So it's telling us that CLT is already met. So we don't have to ask ourselves any questions now, in order to use CLT, right? I don't have to worry about sample size. I don't have to worry about anything because it's telling me that the actual population is normal. So I can use, the probability tools. Okay, what is the probability that the finishing time of a single random selected runner is within 10 minutes of the population mean? All right, so first things first, you guys have to take the key numbers, right? We're looking for key numbers. What are they? Average, and we're looking for standard deviation. All right, we're going to take those numbers and we're going to use it for A, B, and C, right? With also the knowledge that it's normally distributed, which means we can use our calculators, right? So taking the knowledge that our standard deviation is 16, we're now going into this problem, which is what is the probability that a single random selected runner is within 10 minutes of the population mean? So what we're going to do is we're going to put in 1 here, right? And we're going to take the square root of 1, which is just 1. So 16 divided by 1 is 16. And now what we're going to do is we're going to go into our calculator and punch in the numbers to find what's the probability that the runner will be 10 minutes of the population mean. Well, let's just clarify something here. So the population mean is 91, right? 10 minutes of 91 would be 81 on one side, and 91 plus 10 is 101. So we want to know the probability that the sample, right, will fall between 81 and 101, okay? So we go over here. We go to our calculator, and the average is 91. The standard error is 16, right? And we're going to go and we're going to put that in between 81 and 101. Now look at the curve, right? So the area is already, it's kind of small. It's like not even 68%. Remember that here and here are the one above, one below, and that's 68% using the empirical rule. If you don't understand what I'm saying, don't worry about it. You can just look at the output from your calculator, which is 0.468. So we go back to our problem. So the answer is 0.468. And then what you want to do is you want to round it to the nearest hundredth. So the answer is 47%, right? Is the probability that it's going to be 10 above and 10 above, 10 below your the mean, right? So that's how we came up with that probability for one runner. Now, if we have 9 runners instead of 1, we're going to take our n and we're going to plug it in. We're going to plug it in for it 9. And then what we're going to do is we're going to do 16 divided by the square root of 9, which is 5.33. So now what we do is we go into our calculator. And the only thing we have to change is 5.33. There you go. Look at that. Look how big that is, right? So our sample size got bigger, and so did the probability that we would be, 10 above or 10 below within the average runtime, right? So the answer was 0.939. All right, so let's go here. 0.939. So what you're going to do is you're going to round it, 0.94. So it's 94%, right? That are for our 9 runners, right? The average time is going to be 10 above, 10 below, right? What does that mean? So let's look at the next question. All right, our next question. Compare the two probabilities. What does it tell you about the benefits of a large sample size for estimating? All right, so first things first, actually, what's interesting is two ideas over here. First of all, I want you to understand this. The larger the sample size, the smaller the standard error. Why? Because our standard deviation is getting divided by the square root of our sample size. So the bigger this gets, right, the smaller the standard error is because you're dividing it by a larger number, right? So the smaller the standard error is, the more precise our calculations are about the mean, right? Also, the larger the sample size, the closer to the mean. So the larger the sample size of our sample, the closer we get to the mean. Okay. Now let's do a whole different problem. All right. According to one very large study done in the United States, the mean resting pulse rate of adult women is about 74 beats per minute, and the standard deviation of this population is 13. The distribution of a resting pulse rate is known to be skewed right. Yeah, I mean, the standard deviation is pretty big, right? And so it's skewed right. This changes the game. Before, right, in this problem, it was made clear to us that it was a normally distributed population, which meant that we did not have to go through the 3 rules every time they wanted us to look at a sample to come up with the probabilities. We will have to go through those 3 rules for each of these probabilities now. So let's see. All right, let's do the first one. A. Suppose we take a random sample of 36. So remember, random, check, right? Our sample size 36 is bigger than or equal to 25, so check. And we were told it was a big population, so we can go forward with A, right? What is the approximate probability that the average pulse rate of this sample will be below 71 or, okay, so 71 or 70 above 77? Okay, no problem. Remember that we have to take our standard deviation, which was 13, and we're going to have to take the square root of our sample size, which is 36. Mr. Calculator to find out what that is. So I'm going to go to Desmos Scientific. Let me start from scratch. I'm going to pump in AB, right? I'm going to put in 13 on the top, square root 36 on the bottom, and I get 2.16 repeating, right? Go over here, change the standard deviation to 2.16666, change the mean to 74. Now they didn't want between, they didn't want above or below, they wanted outside. And they said 71 and 77. So look at that, right? So that's below 71, above 77. Good, that's what they wanted. I go to my calculator, it says 0.16. So my answer is 0.166, right? This is bigger than 5, so it becomes 0.17. 17% chance, right, that it's either going to be below or above 71 or above 77. Okay? All right, next one. Can you find the probability that a single adult woman will have a resting pulse rate more than 3 beats per minute away from the mean value of 74? Okay, so remember, it was skewed right, so it wasn't normally distributed. Not a big deal if the sample is random. Can you find the probability that adult women? It doesn't say that it's random, right? And then the other thing that it fails is it's a single adult woman. So single is definitely not, right, greater or equal to 25. So this is out. So I didn't change this to B, but so we can't do it. CLT requirements, right? Requirements. Oh my God. I feel like I spelled it wrong. Are not met. Right? Or you can CLT not met. You're done. All right, that's it. For the rest of the week, we're going to just practice finding these probabilities and checking for CLT. All right, until then, bye bye.